Hello everybody, today we'll talk about sums of random variables and a central limit theorem. So this is kind of part three of the probability theory. Okay, part three. And this is the final part. So in theory, when we finish this part, next week we'll start statistics, inferential statistics. This is the final part in our probability theory, okay? So what do I mean by sums of random variables? Okay, let's read here. Suppose x and y are two random variables. 1 second here, okay, x and y are two random variables. Then z equals x plus y is also a random variable. What does this mean? This is saying to take each possible value of x and add it to each possible value of y. Each value for all possible sums creates the outcome space for the variable z. Because there's a probability associated with each possible value x and y, then their sum also has a probability associated with it, and their sum is called z in this case, okay? So basically, this is the way to think about it. You know, x is a random variable, so it can take on some numbers. Maybe the numbers 1 through 6 if it's the die roll, right, or something like that. Suppose y is like a coin flip or something like that. It takes the numbers 1 or 2 or something like this, okay? Then what you're looking for in this case is to take, because x can take on some values and y can take on some values, you just add all possibilities together to get z. So x can be 1, y can be 1. This is one possibility. X can be 2, y can be 1. X can be 1, y can be 2. Perhaps it depends on what the random variables are exactly, okay? But then your outcome, z in this case, will also be a random variable based on what x and y, based on those possibilities of x and y, okay? So some values of x and y are more likely to occur. Therefore, their sum will also be more likely to occur. It will be a more likely portion of z in this case, okay? Some values of x and y are less likely to occur, and therefore their sum will also be less likely to occur. Okay, so z will have a lower probability for their sum in this case, okay? So where is this used? Why is this sum of random variables important? This is actually very, very important because this is used in what's called the distribution of the sample mean. In the book, they call it the sampling distribution. The sampling distribution, okay? The central limit theorem, t-tests, and other hypothesis tests. So this is like the, it's very, very important, the sums of random variables, to understand what is happening here, okay? So here is an example, a coin flip. Given a coin, suppose I assign heads to equal 1 and tails to equal 2, all right? Then suppose I flip it twice. Then I want to add the total from both flips. Okay, it's like the sum of the two random variables. Coin flip 1 is one random variable and coin flip 2 is the other one, okay? Because each of the two coin flips is a random variable, I want to know the probabilities associated with the total. The random variable of the first coin flip is identical to the second coin flip, and so what are the probabilities of the total? Let z be the random variable associated with the total, and z will tell me the outcome space of the sum and the associated probabilities of the outcome space. Okay. Okay. Again, how do you compute z? Okay. Assign 1 for heads, 2 for tails. Okay. And x1 represents the first coin flip, x2 represents the second. Okay. And so the first thing to do is tell me all possible values that z can take on. If x1 can take on 1 and 2, and x2 can take on 2 and 1 and 2, then what? The minimum possible value that z will be if x1 is 1 and x2 is 1. In this case, z will be 2. Z can be 3 when x1 is 1, x2 is 2. Or x1 is 2 and x2 is 1. That's when z can be 3. And z can be 4 only when x1 is 2 and x2 is 2. Z can be 4. Because if 2 heads are landed, then their sum is 2. If a head and a tail is landed, then their sum is 3. And if a tail and a tail is landed, then their sum is 4. Okay? Okay, like this. What are the probabilities associated with z? Intuitively, to get the probability of 2, both flip and 1 and 2 have to be heads. And so multiply the probabilities together, like this. 1/2 times 1/2. To get a total of 3, then one of the flips will be heads and the other one tails. This probability is going to be 1/2 because there are 2 ways it can occur. Either flip 1 is heads and flip 2 is tails. Flip 1 is tails and flip 2 is heads. Adding the probabilities, or 1/4 twice, will be 1/2. Then what is the probability of getting a 4? This can only happen if both flips are tails. And this is a 1/2 chance that the first one is tails and a 1/2 chance the second one. Again, I multiply those probabilities together. Okay? Okay? To get z. Okay? Okay? So notice, before I continue on, let me draw the distribution of z. Okay? And what it will look like. Okay? Okay, so I just got out the drawing board here. Okay? So let me explain to you what is happening. Okay, so you got this random variable, it's x1. And it looks something like this. It has a probability of getting a 1, and it can take on only the values of 1 and 2. It cannot take on any other values. So again, this is called a discrete random variable. And the probabilities to get a 1 is 0.5. Okay, like this. And you can put a dot here, and sometimes it's easier to just put a line to see it better. Okay, and a dot here. So it's 0.5 and 0.5. Okay. And then separately, I have another random variable. Okay. And it can also take on the values 1 and 2. Okay. Okay. Like this. And the probabilities associated with each one of them are also 0.5 each, like this. Okay. Another thing to say is that these variables are independent. That means whatever realization I get in x1 is not going to affect what happens in x2. So let's say if x1 lands on a 1, this is not going to make x2 more likely to land on a 1 or a 2. So this is called independent. In this case, they're independent and identically distributed, because the distribution is a 0.5 on 1 and 2 and 0.5 on 1 and 2. So they're independent in a sense. Whatever happens to one of them is not going to affect what happens to the other. Okay, so they're called independent random variables. And this is also an important thing. I don't mention it too much in the lecture, so people don't get confused on what is this independence. But it's basically saying that the impact of one of them is not going to affect the impact of the other. Whatever happens to one is not going to affect the other, okay? Okay, so this is x1, okay? Yes. And anyway, if I add x1 plus x2, I'll get some kind of a distribution z. Okay, and distribution is going to look like this. Okay. Okay. And again, I put here a probability, and I put here x. Okay, for just x values. And these values will be z here. Or these are all possible values that z can take on. So the first thing to do is to tell me what possible values can z take on here. Well, I'll tell you, z can only be 3 possible values. Z can be, because it's the sum of 2. So x1 can take on the value of 1, x2 can take on the value of 1. So the minimum z can be is 2, because 1 plus 1 is 2. And then z can also be 3, because x1 can be 1, and then x2 can be 2, which equals 3, or x1 can be 2, and x2 can be 1, which also equals 3. Okay? And lastly, the maximum that z can be is 4, because x1 can be 4, can be 2, and x2 can be 2. So 2 plus 2, right? 2 plus 2 is 4, like this. Okay? So, so far so good. Now, the next step is to get probabilities. What is the probability of getting a 2? Because the next step is just to give me the distribution here. And in theory, if this is a random variable, its probabilities have to sum up to 1. Okay, so I get some probability of getting a 2, some probability of getting a 3, and some probability of getting a 4. So how do you get these probabilities? Well, the first thing you do, okay, is to look. Okay, the probability of getting a 1 is 0.5 on x. This is the only way I can get a 2. If I get a 1 on the first one and a 1 on the second one, then 1 plus 1 is 2. Right? So what is the probability of getting a 1? Okay, so z, probability that z equals 2, right, this is how you write it, is probability that x1 is 1, okay, times, and I need to multiply, obviously, because I have a half a chance of getting a 1, so a 50% chance I get a 1 on the first one, times a 50% chance I get a 1 on the second one, okay? Like this, okay? And that's 0.5 times 0.5. And that's equal to 0.25, like this. Okay, everybody? Are you following me here? I need to multiply the probabilities together. I need to multiply this 0.5 times this 0.5. Okay? And so that the percentage chance here will be 0.25 for getting a 2. What about to get a 3? Probability that z equals 3. Well, there's 2 ways this can occur. Either I get a 1 on the first one and a 2 on the second one, because 1 plus 2 is going to equal 3. Okay? Or I can get a 2 on the first one and a 1 on the second one. Okay? So this is what? What is the probability of me getting a 1 and a 2? A 1 and a 2, right? So this is probability that x1 equals 1, okay, times probability x2 equals 2. So this is one way it can happen. I can get a 1 on the first one and a 2 on the second one. And the probability of this happening is probability of x1 equals 1 times probability of x2 equals 2. You multiply the probabilities together. This is the probability of the whole thing occurring, of getting a 1 and getting a 2. Getting a 1 on the first one and getting a 2 on the second one. Is this probability here, okay? Plus, there is another way it can occur, though. I can get a 2 on the first one and a 1 on the second one. Okay, so this is what you write here. Okay, watch. Probability x1 equals 2, right? Times probability x2 equals 1, like this. And this is the percentage chance that I get a 2 and a 1. This is the percentage chance of me getting a 1 and a 2. Does that make sense? And what is this? This will be .5 times 0.5 plus 0.5 times 0.5, which equals to 0.25 plus 0.25, and that's equal to 0.5 exactly. So this answer is 0.5. Okay, and that makes sense. So getting a 3 is actually twice the probability of getting a 2, because there's 2 ways it can occur. There's 2 ways it can occur, and each one is like 50-50, because this is fair, okay, like this, okay. Lastly, what about the 4? You can try and figure out on your own. I don't have a lot of space here, but I'll write it here. Probability of z equals 4. Okay, is equal to probability that x1 is a 2 times probability that x2 is a 2. It can only happen one way. Both of these numbers, x1 and x2, have to be 2. Okay, and that's equal to 0.5 times 0.5 equals to 0.25. Again, this is the exact same probability of getting a 2, like this. And so this is the random variable z, and this is the distribution of z. I have the outcome space here, and I have the probabilities, okay? Okay. So this is the very basic idea behind sums of random variables, okay? Okay. Okay. Let's move on now. Notice that when z is x plus x, in this case it was x1 plus x2, this is not the same as z is equals 2 times x. Notice, although the random variables in the previous example have the exact same distribution, called an x, but in theory they're different random variables, x1 and x2, because they're 2 different coin flips, okay? But z equals x plus x is not the same as z equals 2 times x, because they're actually different. The random variables, even though they have the exact same distribution, they actually indicate 2 different things. They indicate the first coin flip and the second coin flip. It is worth to actually call them x1 and x2 rather than just giving them the same name, because they have the same distribution. Okay, so just make sure you don't do this. Okay, when adding random variables, I'm taking all possible values of one variable and adding them to all possible values of the other. On the other hand, when I multiply a random variable by a constant, I'm multiplying all possible values of one random variable by a constant, in this case 2. Okay. Thus, z equals x plus x equals 2x when both x's take on one of the same values all the time. In this case, when the first x is 5, the second x will also be 5, then this will be true, but this will only happen, which we haven't talked about this, when x1 and x2 are not independent, but they're highly correlated. Actually, they're correlated with a correlation of 1. And in this case, this will be the case. It will be true that z equals 2 times x. Okay? And they're highly correlated, but don't worry about this for now. Okay? So what is the general method of summing random variables? I just showed you how to do it with an example, right? And so if you want to sum two random variables, you first have to get the distribution of the n outcome space of z. So first you get the outcome space. The outcome space of z is obtained from the sum of the total of any two outcomes. Okay? To obtain the PMF of z, simply add the probabilities associated with the same totals. Okay? Okay? Yeah, the PMF. Okay? So I'll give you another example with a die roll here. Okay? I'm playing Monopoly. It's a game. It's a board game. If you guys don't know what Monopoly is, it's like a board game. In the game, I roll 2 dice and take their total. What are the possibilities for the total and what are their probabilities? Let x1 be the number on one of the dice and x2 be the number on the other die. Then z equals x1 plus x2 is a random variable representing the possibilities of the total. What is the outcome space in the distribution of z? So basically, as I'm playing Monopoly, I roll 2 dice, and you know how in the game you have to sum the 2 dice together. So that means when you sum them, I'm not going to be able to get the numbers 1 through 6 now. I'm going to be able to get the numbers 2 to 12. 2 is the minimum I'll be able to get, and 12 is the maximum. And I can get 2, 3, 4, 5, 6, 7, all the way to 12. And I'm curious to know, what are the probabilities of the numbers 2 through 12? And this will give me the distribution of the total, which is z. Okay? And you guys have played Monopoly, and you know that getting a 2 is rare and getting a 12 is rare. But getting numbers close to the middle, like 6 or 7, is most common, right? 6, 7, 8, these are the most common totals that you'll get. If you didn't know this, I'm telling you it's the case. Okay. So to proceed, what do? You first get what's called a bivariate distribution of z. This will get us the outcome space and distribution of x1 and x2 when we can sum up the probabilities of the same possible outcomes to get z. Okay. So this is what you do. You get all possibilities of getting the first die here. The numbers are 1, 2, 3, 4, 5, 6. These are what's possible. Then you get the probabilities of getting what you can roll on the second die. Okay, and then what you get is you get the bivariate distribution. This, we haven't talked about this yet, but this is a distribution that tells us probability of occurrence of one of the dies and probability of occurrence in the other. So this is saying get when the die equals, the first one equals 1 and the second one equals 1. What is this probability? It's 1 times 6 times 1 over 6. So 1 over 6 times 1 over 6. Okay? And this is, for this to occur, it's 1/36. Okay? And then this is saying, what is the probability of me getting a 3 on one of the dice and a 4 on the other? Again, it's 1/36, because like in order to get a 3, it's 1 in 6 chance, and 1 in 6 chance to get a 4 on the other. It's 1 in 36, okay? So again, let's read here. The numbers in the squares indicate that the probability of rolling a particular value on the first die and rolling a particular value on the second die, any value, is 1 times 6 times 1 times 6 is 1/36. To sum of the probabilities of the same total, simply add the diagonals to the distribution and sum y. So this is what you do. What is the probability of me getting a 2? It's just 1 and a 1, so I multiply this by 100. What is the probability of me getting a total of 3? There's 2 ways it can occur. I can either get a 1 and a 2, or I can get a 2 and a 1. So I add these in the diagonal. Okay, and this is it's twice as much getting a probability of a 3. What about getting a probability of a 4? There's 3 ways it can occur. I can get a 1 and a 3, a 2 and a 2, or a 3 and a 1. 3 ways it can occur, so I have to add up this plus this plus this. Okay. What about getting something like a 5? How many ways it can occur? It can occur getting a 1 and a 5, getting a 2 and a 4, getting a 3, getting a 4 and a 1, right? It's a 5. Getting a 2 and a 3, getting a 3 and a 2, and getting a 1 and a 4. So there's 4 ways I can get a 5. Okay, and again, I add the probabilities together to get the total for 5. I use the same logic, and this is what the distribution I'll get for the Monopoly rolls. So what is the highest probability of getting? A 7. There is almost a 20% chance of getting a 7 when I roll the dice, okay? And the lowest probabilities are getting a 2 and a 12. These are 1 in 36 chance, like 2.78% chance of getting a 2 and a 12. And you probably knew this when you played Monopoly. You knew that 2 is very rare. 12 is also rare. But getting numbers in the middle, in terms of totals, is more common, right? So this is intuitive. Notice something. The distribution of the total, which is the one here, looks normal, looks like a normal, with a peak at 7. So then the sum of 2 discrete uniform random variables, in this case, the 2 die rolls are uniform discrete random variables, as we saw from the first part, right, of the probability theory. So the sum of 2 discrete uniform random variables was the 2 dice rolls created a normal looking discrete random variable. It turns out that the distribution will be even more normal looking if it was the sum of more die rolls instead. So the more die rolls I sum up, let's say I sum up 10 different die rolls, the distribution will have numbers. The minimum we want is going to be 10 now. It's going to be 10 is the minimum if I sum a 10, because this is the probability of getting a 1 in all 10 dice, right? If I roll the 10 dice, probably that will show up as 1s. Okay, it will be very, very small. It's 1 in 36 times 1 in 30, or 1/6 times 1/6 times 1/6, right? And you can do this, and you'll get this probability of getting a 10. And getting then the maximum, which is 60, is probably rolling a 6 on all these 10 dice that I roll. Again, this is very, very rare. Okay, but probabilities in the middle are more common. So probabilities of getting a sum total of around, in this case, 35, between 30 and 40 somewhere, will be more common intuitively. Okay, because there's way a lot more ways that this can occur. Okay. Okay. Let's move on. So you got the logic here. Just make sure you got the logic of what you're doing here. Again, this is very important. Okay. And the distribution of the sum of the two dice, call it y in this case. I choose another random variable name. Is going to look something like this. Again, it looks a little bit like a normal. Okay. This is okay because just keep that in mind. What about adding multiple random variables? How do you do it? Z equals A plus B plus C. How do you add A plus B plus C? You can first add A plus B, call it X, and then separately do the next computation, X plus C. Or you can add B plus C, call it Y, and then you can add Y to A. Okay? Or you can first add A to C, call it W, and then W to B, whatever you want. So actually the associative property holds with random variables. I don't care which one I add to what first. Okay? Okay? Or I can actually add all three together and multiply all their probabilities together for a particular number. And this is what I do here. So suppose, for example, there are 3 coin flips with heads equals 1 and tails equals 2. Okay? Again, this is the same exact example from the first time. There are 3 different coins though. Let the coin flips be random variables represented by x1, x2, and x3 respectively. However, their numbers are a bit unfair. So flipping the first coin, okay, I'll get most likely tails. 90% chance I'll get tails on the first coin flip. On the first one, I'll get heads with 10% chance. On the second one is a fair coin, 50-50, and the third coin is most likely going to be heads and less likely going to be tails. What is the sum of these 3 random variables? In other words, if I flip each coin and take their sum, what do I expect to get? This is the random variable z. So first add x1 and x2, and then add x3 to these. Also try adding x2 and x3 first, and then add x1 to the total. What do you get? So think about what you are going to do really quickly. Okay. So let's see what the answers are. Again, you can add any 2 of the coins, obtain a random variable, and then again add this random variable to the third coin. Or here's another way. Use a multivariate distribution. In this case, add all 3 together at once. It's also possible. What you're going to use is a multivariate distribution. This is similar to the bivariate, but with 3 or more random variables. So this is saying, what is the probability of me getting an x1 and an x2 and an x3? Okay, so probably I'm getting an x1 equals 1, x2 equals 1, x3 equals 1. So getting heads, heads, heads in this case, okay? And this is what we'll be doing. So first start with the totals. Adding coin 1 and coin 2, the possible totals are 2, 3, 4. Adding coin 3, the possible totals are 3, 4, 5, 6. Where 6 represents the sum of all coins that land on 2 in this case. 3 represents that the sum of all coins land on heads. 4 represents 1 coin landing on tails and 2 coins landing on heads. And 5 represents 2 coins on tails and 1 coin on heads. Let the sum be called z. So probability that all heads is probability that z equals 3. which is 0.1 times 0.5 times 0.7. How did I get those numbers? I just look here. Probability of heads for the first one is 0.5. Probability of heads for the second one is 0.5. Probability of heads for the third one is 0.7. Okay. And what about the probability of tails, or z equals 6? 0.9 times 0.5 times 0.3. It's 1 minus those, right? Okay. Okay. What about when z equals 4? There's 3 ways that this can occur. I can get 1 and 2 are heads, 3 is tails, 2 or 3 are heads, 1 is tail, 1 and 3 are heads, 2 is tails. So these are the probabilities of each one of those. I add them up together, those probabilities, and this is the probability of getting a 4. Now, of getting a 5, again, there's 3 ways it can occur. Again, you multiply the probabilities together, and you add them up to get a 5. Adding up probability is equals 3, 4, 5. Is equals 3, 4, 5, and 6. It should be, right? I don't know why there's 7 here. I just correct it here, okay? In this case, the last one is 5, right? The first one is 3 and 6, like this. And then it's 4, and these are the corresponding probabilities of those, okay? Like this. And this is what the distribution is going to look like of this die roll, okay? Okay, so now we went sums of discrete random variables. What about continuous random variables? Is there a way to add continuous random variables? As you can see, all the examples were done with discrete random variables because there's rules I can do. I know what to do with discrete random variables. I just showed you, right? However, sums with continuous random variables generally require calculus. However, there are some rules. For example, if x1 and x2 are normal, then their sum is also normally distributed. Z will also be normal with having a mean that is equal to the sum of the means and a variance equal to the sum of the variances. This is a general rule for normal distribution, okay? So x1 and x2 are 2 different normals. They don't have to be the same distributed normals. 2 different ones, okay? Now, in general, if you're not sure what to do, you can try an experimental technique that I explain in class. Sometimes I explain it, okay? So basically, what you do is you make the variables from continuous, you can convert them to discrete, okay? You can convert them to discrete random variables. This is what you can do. And basically, you take the averages there and you make them discrete, but it's don't worry about this now. If you're really interested, I can tell you what to do later, okay? This is not important for this class or the test, okay? Let's move on. The sample mean. This is called the sampling distribution in the book, the sampling distribution. But this is the distribution of the sample mean, okay? Suppose instead of taking the sum of 2 random variables, I'm interested in their average. This is the sum of n random variables divided by the number n. So if n is 2, if I just sum 2 random variables, I have to divide by the number 2 after I sum them. Okay. So this means instead of the distribution of the sum of the random variables, I'm interested in the distribution of the mean of that sum, or the average of that sum. Okay. From the coin flip example, this is the sum of the 3 flips divided by 3. What does this distribution look like? The answer: the distribution looks like the distribution of the sum, except that it is tighter because I'm dividing by the number 3. So this is just a transformation of the new random variable, right? Suppose I add up x1 plus x2 plus x3 equals z. This is, and z is the sum of x1 plus x2 plus x3. Now, if I divide z by 3, I'm just doing a transformation. Okay, the new random variable z divided by 3, I'm just doing a transformation there. And the new transformed random variable is the distribution of all of possible averages of x1 plus x2 plus x3 divided by 3. Okay? Of all possible averages. That is a distribution, because if I sum all the 3 numbers up, right, and I divide by their total, in this case 3 random variables, right, I sum up, I divide by 3, I get a distribution of all possible averages again, okay, of those 3 random variables. If you have done this successfully, you've just computed the distribution of the sample mean, and again, this is called a sampling distribution. Okay. Moving on. Let me show you some mean and variance rules here for sums of random variables. Given random variables called w, x, y, and some constant parameters a, b, c. Okay. Let z be aw plus bc plus cw, where aw means a times w. Okay. We call expected value of x and variance of x mean, expected value and variance of x respectively, right? Then, if I know how I summed up the random variables and how I got z, okay, and I know their variance and expected values of the random variables, w, x, and y, if I know their expected value and variances, I can get, by these rules here, I can get the expected value and variance of z. This is what it's saying here, okay? To see why the parameters are squared, recall that if w1 equals aw, and variance of w1, again, is a squared times variance w, in most applications, the parameters a, b, c are generally seen to equal 1. Okay, in most applications. So don't worry about these parameters. You can just put ones here if you're just adding normal random variables. Okay. For example, if I just want to add w plus x plus y equals z, I set these a, b, c to ones for simplicity. Okay. Okay. So moving on. Suppose there are n identically distributed random variables. They're also independent from each other, which don't worry about it, what that means for now, okay? So x1, x2, x3, dot, 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 xn. So x1 through xn. Each one of them is identically distributed and independent from each other. Each one has a mean, expected value of xi, or the ith one, has a mean of mu and a variance of sigma squared, is the variance of each one of them. Then their sum, x1 plus x2 plus x3 plus to xn, call it the sum of the x's. You can call this z if you would like, the sum of the x's. And this sum is a random variable also. It's a new random variable. Okay? And this new random variable, the sum of them, in this case, is approximately normal. And the approximation gets better and better as more variables are summed as n grows. Okay? Okay? This is what it means. By the mean and variance rules, the expected value of the sum is n times mu, because this is the expected value of the first plus the expected value of the second plus the expected value of the third, dot dot dot, plus the expected value of the nth. And there's n of them, n of these random variables. So this is n times, so this is mu plus mu plus mu plus mu, all the way to n. So this is n times mu. And similarly, the variance of this thing here is the sum of the variances of each individual one. So this is the variance of the first, which is sigma squared plus sigma squared plus sigma squared plus sigma squared, all the way, there's n of those. And so the variance of the sum is n times sigma squared. And therefore, by the central limit theorem, if for a big N, this sum of the x's, which you can call z in this case, for example, is distributed normal with a mean of n times mu and a variance of n times sigma squared, like this. Transforming to standard normal, you just have to, what do you have to do? If you have the random variable here, you subtract the expected value of the random variable, or you subtract this, and you divide by the standard deviation, or just the square root of the variance. Okay, and this is the square root of the variance. And this should be a normal z, normal 0, 1. So I can transform it into a z. Okay? Suppose instead of the sum of the random variables, I take their average. So I sum them all up again, but then in the end I divide by n, like this. Call this sum of x divided by n, call this x bar. X bar is approximately normal as well, since it is just a transformation of the sum of x. And how do I transform it? I just divide by a number, in this case n. And you remember those transformations. If I divide a normal by a number, it's still normal, but a tighter normal, if you remember, okay? So this is just a transformation of the sum. I just divide by n. So what is the expected value and variance of x bar, or the average? Well, I just take the rules, the mean and variance rules. So the expected value of in this case, expected value of x bar, the expected value of the sum of the x's divided by n, which is n times mu divided by n, which is just mu. And the variance of x bar is I have to square the constant. I have to square the constant, which is 1 over n. I square that. And then I have the variance of the x's, okay? Which will then just be, in the end, will be n times sigma squared divided by n squared, which will be just sigma squared over n. Therefore, the sum of the x's divided by n is equal to, again, x bar, and this is normally distributed with the mean of mu and a variance of sigma squared over n. Transforming to a standard normal, again, I subtract the mean divided by the standard deviation, and I get a normal, which is z. Okay? Like this. I'll give you an example. This is the distribution of the sum of two dies, right? x1 plus x2. You remember this from the earlier slide. A very small probability of getting a 2 and a 12, high probability of getting a 7. Okay? What will be the distribution of the sample mean? In this case, I roll the two dice and I divide by 2. So if I get a 12, if I get 2 6s, I get the average. So what is the distribution of the averages? All possible averages that I can get. Well, the biggest average I can get is a 6. That means when both dice were 6. And the smallest average I can get is a 1. Because that means that both dice were 1. Or I just sum them up and divide by 2. Okay? And how would this distribution look like? Well, it's the same as the distribution of x1 plus x2, but I just divide by 2. It's just going to be a transformation of this. Okay? So I divided by 2 to get the, again, to get the probabilities of the averages, of all possible averages. Okay? And so the most common average is 3.5. This is when the total is 7, because I just divided by total by 2. And the least likely average is a 6 and 1. Okay? Exactly the same, I just divided by everything by 2. Okay? Okay, so here is where the lecture ends. Please take a break. Listen to the lecture a couple more times. Make sure it makes sense. And now we'll move on to the questions. Okay? Okay. So here, I flip two coins once. Let the first coin be represented by the random variable x1. And let the second coin be represented by the variable x2. Okay? Also, as random variables have to have a numeric outcome space, let heads be 0 and tails be 1 for both coins. The PMFs of the two random variables are, so for the first coin, there is a 30% chance, or a 0.3 probability, of getting, in this case, heads, and a 0.7 probability of getting tails. So in this case, tails is a lot more likely to happen. 70% of the time I'll get tails, 30% of the time I'll get heads. Again, the coin is not even. It weighs a bit more on one side. In this case, it weighs more on the head side, because when the heads lands, it shows tails. All right, so it weighs a little bit more on the head sides in this case. And the second coin is even more likely to get tails with a 0.9. So it's not a fair coin at all. So 90% of the time I'll get tails on the second coin. Okay? And 10% of the time I'll get heads. So it weighs even more on the head side, this coin. Okay? So it's not fair again. Okay? Even worse than the first one. Define z equals x1 plus x2. What is the PMF of z? Well, I'll tell you what to do here. Okay, let's see. Let's just go back to the drawing board. Okay, like this. And I'll tell you how to answer those questions. Okay, like this. Okay, watch. So here I have two coin flips now, x1. And this will look something like this. Okay, and this will be 0. Now it technically should be here, but I want to see it, so I'll put it here. This is 1. So this kind of represents your heads, and this represents your tails. Okay, like this. And to get a heads is a 0.3 probability on this one. So 30% chance of me getting a heads. Okay, and to get a tails is a 0.7 probability. Okay, like this. Something like this. It's almost twice as high. More than twice as high. Okay. And then for x2, it's even worse. Getting a heads, getting tails. So getting heads is 0.1. And getting a tails is 0.9. So very high probability of getting a tails. And so guess what? When I sum those up on the total, I'm going to be more likely to get 2 tails, a lot more likely than 2 heads, or maybe a head and a tail. I'm very not likely to get heads. I'm probably most likely to get two tails than anything. The first one being a tail and the second one being a tail. So in this case, what is the probability of getting HH? This is kind of the this is what's called the bivariate distribution here. Okay, HH. So this is what is going to be. I'm not going to write all the probabilities out, but it's going to be 0.3 times 0.1, which equals 0.03, like this. And what is the probability of getting a head, tail, okay, plus probability of getting a tail head, because the sum of the total, in this case, let's first get the outcome space of Z so we don't get lost. So getting 2 heads is going to be a 0. The 0 plus 0 is going to be 2 heads. This, okay. So this represents, I'll just put it here, HH. So you know that 0 is HH. Then I can get a total of 1. And this is 2 ways it can happen. It can be heads in the first one and tails in the second, or it can be tails, heads, like this. This is what 1 represents. One of them has tails and the other one has heads. And this is 2 ways it can happen, okay? And then 2, it's only 1 way it can happen. I get tails, tails here, okay? So, if you want to be very precise, let's see, Z equals 1, not 1, 0, is equal to this. Probably Z equals to 0. In this case, it's 0.03. Very low chance I get 2 heads. This is intuitive because they have low probabilities of occurrence anyway. So a 3% chance on this happening, okay? And then here is probability Z equals 1. This can happen when I get heads, tails plus tails, heads. So me getting a heads in the first one and tails in the second is going to be what? 0.3 times 0.9, this, plus me getting a tails on the first one, plus me getting a heads on the second one, right? And this probability is let's just make sure everything's straight. There's no errors. So 0.7 times 0.1. And what is this equal to? This is 0.27 plus 0.07. And this equals to what? Okay, watch here. 0.34. So 34% chance I get one of them as heads and the other one as tails. 34% chance, okay? This is not bad. Okay? And I put here 0.34. Okay? And lastly, because I'm running out of space, okay, let's compute probability that Z, okay, probability that Z equals 2. And this can only happen when this is probability of tails, tails. Okay? And when is this going to happen? When the first coin is tails, which is probability of 0.7, and the second coin is tails. Again, this is very, very likely to happen, which is going to be 0.9. Okay? And this is going to be 0.63. So in this case, the most likely outcome, because the coins were not fair, the most likely thing that's going to occur if I flip it twice, or if I flip each coin once and sum the total, let's say, okay, is me getting 2 tails with a probability of 0.63. It means more than 50% of the time, the majority of the time, I'll get two tails. Okay? And so the distribution will look something like this. Okay? Are you guys seeing how I did this math? Just go back. This is what you do. If you're not getting it now, go back, look through the lecture. I did a similar problem with those probabilities were 50-50 everywhere, right? Think about what I'm saying and doing, okay? Please. Then, right, watch. I'll double check my answers. The total should be 1 here. Should be 1. Is this 1? 0.03 plus 0.34. In this case, 0.03 plus 0.34 plus 0.63 probability. Well, 0.03 times 0.34 is 0.37. And 0.37 times plus 0.63 is exactly 1. So you put a check here that these numbers look up, they're reasonable numbers, and they add up to 1. Okay? Okay. Okay. I explained everything here. Okay. 1 second. Okay, let's see what this one says. Suppose I roll a fair die 10 times. I take the sum. What is the average? What is the probability of getting a sum less than 30? Now suppose I take the average of the 10 rolls. What is the probability of getting an average of more than 3.8? So this is another problem. It's a little bit longer. And the idea here is not to sum all the die rolls up. You can do it manually, like I did it, which is going to take you a very long time to do, because there's 10 different dies. I need to get probabilities of each one of them. Remember, I did it in the lecture for 2 rolls. Take it when you, like for Monopoly, take it, you sum 2 of them. Okay? This took a long time. 10 is going to take a very, very long time. Okay? So, 1 second. Okay, so I'm back now. Okay. So the whole idea then, in order to be able to answer these questions, I will first have to compute the expected value and variance of each roll. Okay, because each time I roll it a total of 10 times. Okay, each one of the rolls will be the die roll distribution, in a sense. It just have a probability of occurrence of getting a number, and each one will have an expected value and variance. So this xi represents any is random variable that represents any of the 10 rows. And so I compute the expected value as 3.5 of just one of the rows, which is reasonable. And the variance is 2.9. Okay. Okay. Now, what is the probability of getting a sum less than 30? Well, from that central limit theorem, I know that the distribution of the sum is approximately normal. And in particular, the sum of all of them, because what happens is that each time I roll the die is like a random variable, because I don't know what I'll get. And the random variable, each time I roll, is at the same distribution as the die roll. So the first time I roll it, I don't know what I'm going to get. It'll be the numbers 1 through 6, and I know the probabilities of those, but I don't know what number exactly that I'll get. And the fifth time I roll the die, again, is the exact same distribution. And the 10th time I roll, I get this exact same die roll distribution. And then the idea is, what is the probability of the 10 rolls? Give me all possibilities. Give me the outcome space of the sum of them. So each time I roll can be seen like a random variable in itself. Okay? Each time I roll. Okay? And so give me the probabilities of the sum of all 10 rolls. And so this is like summing 10 identically distributed random variables. And this is like summing 10 die rolls instead of 2. In our example, we did 2. Now I'm going to do 10. Okay? Okay? And so the sum of the 10 by this central limit theorem should approximate the normal, because each one of them is identically distributed and independent from each other one. Okay? And so I just computed that. If you see on the PowerPoint, there should be a normal with a mean of n times mu and a variance of n times sigma squared. And so I just, in order to convert to a standard normal to get probabilities, because obviously this normal, I don't know the probabilities of this. If I have a computer or something, or I knew some calculus, I can compute this. Why? What is n? I know n is 10. Mu is 3.5. I computed in the previous slide. Right? I compute the mu is 3.5. I compute the variance of each one of them is 2.9. So I know mu, I know this one, I know n, and this will be an exact normal, or an approximate normal, right? And this kind of normal. Then I convert to a standard normal. Subtract the mean divided by the variance. So I want to know what is the probability that the sum is less than 30. I transform the 30 into the z distribution. All right? This is going to be 30. This is this. I get minus 0.93. So I just look at the table. What is the probability of getting less than 0.93? Negative 0.93 is the same as probability of getting more than 0.93. And I can just look at the tables and it'll tell me. Okay. What is the probability of getting an average of more than 3.8? So again, what is the average? I need the distribution of the averages. In this case, this is just the sum of xi divided by n. And so this is going to be a normal with this mean and this variance. Again, I convert to a standard normal. And if I want probability that x bar is greater than 3.8, I plug in 3.8 for this x bar here, okay? And again, the mu is 3.5. And this is 2.9 divided by 10. I just put in the numbers. And so this should be 0.56. Okay? Okay? So what is the probability that's greater than z is greater than 0.56? Is 1 minus that z is less than 0.56, which is 0.2877 from the table. Again, I can use. Okay, everybody. So again, go through the PowerPoints again if you like. I know this is a bit tricky now. It's getting a little more tricky, but this is kind of as hard as it gets in terms of theory. Okay. The last question, we'll do this in class. Okay. Suppose I have two independent random variables, x and y. I do not know the probability distributions, but I know the expected value of x is 5, variance of x is 10, expected value of y is 7, variance of y is 3. Suppose z is the sum of y and x, in particular z equals y plus x. How much is expected value of z, and how much is the variance of z and the standard deviation of z? Okay? So let's answer those in class, okay? Okay, so this is it for the lecture. Again, let me tell you, something. Obviously, you're going through the lecture at your own pace. Feel free to pause the video, go back, especially in parts you're confused. In class, when I ask you, are there any questions about the lecture? This is when you can ask me, man, I'm confused on this and this, or what does this mean? Okay, feel free to do this, okay? Okay, everybody, bye-bye.